All right, let's jump right in. Welcome everyone, I am so incredibly excited to have you here for this explainer. Today, we're taking a truly fascinating journey to demystify the ultimate blueprint of our universe, the periodic table. We're going to zoom all the way in to see the invisible rules that govern matter, and then zoom back out to understand how literally everything around us is built. Okay, let's dive into this. So, to truly understand chemistry, we first have to wrap our heads around scale. The development of modern atomic theory revealed something kind of mind-blowing. An atom is mostly just empty space. Think about a massive football stadium. If an atom were expanded to the size of that entire stadium, the incredibly dense nucleus at the center, which holds all the protons and neutrons, would be about the size of a single blueberry sitting right on the 50-yard line. Everything else, all that vast empty space in the stands and on the field, is where the negatively charged electrons live. To put a hard number on that, the diameter of an atom is roughly 100,000 times larger than the diameter of its nucleus. Keep that number in the back of your mind, because it's this vast outer volume, this massive swirling cloud of electrons dancing around our tiny blueberry nucleus, that dictates absolutely everything about how an atom behaves, reacts, and bonds. Really, the electrons are the true stars of the show today. Here is our roadmap for this explainer. First, inside the atom. Second, the electron configuration map. Third, organizing the periodic table. Fourth, predicting periodic trends. And fifth, ionic and molecular compounds.
Section 1. Inside the atom. Subatomic particles.
Let's start with a really quick look at the basic building blocks themselves. What's actually wild here is the sheer difference in mass. In the nucleus, we have our protons with a 1+ charge and our uncharged neutrons. They each weigh about 1 atomic mass unit. But look at the electron. It has a -1 charge, but its mass is a minuscule 0.00055 AMU. You'd literally need about 1,800 electrons just to equal the mass of a single proton. Yet despite being almost completely weightless, these electrons determine the chemical identity of the entire universe.
Section 2. The electron configuration map. How electrons fill the void.
Okay, so if electrons are occupying that massive stadium-sized void, they don't just float around randomly. They have rules. And this brings us to our ultimate cheat codes for figuring out atomic behavior. First is the Aufbau principle. Aufbau is German for to build up. It simply means that as we build an atom, electrons will always enter the lowest energy subshell available first, before moving to higher energy ones. But they also follow the Pauli exclusion principle, meaning a single orbital holds a maximum of 2 electrons with opposite spins. And then there's Hund's rule, which tells us electrons prefer to spread out into empty orbitals before they finally pair up. They're wonderfully lazy but highly organized in that way. They always want the most stable, lowest energy arrangement possible. And there's a brilliant diagonal rule that illustrates the exact path they take. Electrons fill the s orbitals, then p, d, and f. Now, as atoms get larger, the energy levels get a bit crowded. You'll actually notice that the 4s orbital fills before the 3d orbital. Why on earth does it do that? Well, as we get further from the nucleus, those inner electrons repel the outer ones, a phenomenon known as shielding. So the 4s ends up being slightly lower in energy than the 3d. Following this filling order tells you exactly where every single electron in any atom lives.
Section 3. Organizing the periodic table. The ultimate cheat code.
Now, let's take that microscopic electron map and zoom out to the macroscopic world. The periodic table wasn't just haphazardly thrown together. It's a direct physical reflection of those electron orbitals we just talked about. The tall columns on the far left and right, those are the main group elements. That's where the s and p orbitals are filling up. That big block right in the middle, those are your transition metals, where the d orbitals are filling. And bridging the gap between the metals on the left and the nonmetals on the right, we have a staircase of metalloids, sharing properties of both. Finally, those 2 rows completely separated at the very bottom are the inner transition metals, the lanthanide-lantactinides, where the highly complex f orbitals fill. The architecture of the entire table is literally just a map of electron energy levels.
So the absolutely crucial point is this. Elements sitting in the same vertical column, or group, have the exact same number of valence electrons. Valence electrons are the outermost electrons. They have the highest energy, and because they're sitting on the very outer edge of our stadium, they are the ones that actually interact with other atoms. It's the loss, gain, or sharing of these specific valence electrons that completely 100% defines how an element reacts.
Section 4. Predicting periodic trends. Radius, ionization, and affinity.
Because the table is perfectly organized by these valence electrons, it acts as a predictive tool. Let's start with size, specifically the covalent radius. Just think of this as the size of the atom. As you move down a column on the periodic table, atoms get bigger. This makes sense, right? Every time you drop down a row, you're adding a whole new shell of electrons further out from the nucleus. But, fascinatingly, as you move from left to right across a period, the atoms actually get smaller. Why? Because you're adding more protons to the nucleus, increasing the positive charge, which pulls that exact same outer shell of electrons in tighter and tighter.
So let's see how that builds into our next trend, ionization energy. Simply put, this is how hard it is to rip an electron away from an atom. If you understood this size trend, you already understand this. A really small atom holds its electrons super close to its highly positive nucleus, so it takes a massive amount of energy to pull one away. But a large atom, with its outer electrons way out in the upper bleachers of our stadium, it loses them much, much more easily.
So we see this beautiful, predictable push and pull. Down a group, atoms get bigger, and it becomes easier to steal an electron. So ionization energy decreases. Across a period from left to right, atoms shrink, and it becomes incredibly difficult to steal an electron, meaning ionization energy spikes. The map tells you exactly how fiercely an atom guards its electrons.
And then on the flip side, we have electron affinity, which is basically how badly an atom wants to gain a brand new electron. The values here are actually negative because energy is released when these atoms manage to grab an electron. The halogens on the far right of the table, like fluorine and chlorine, have highly negative values. They're small, their positive nucleus has a really strong pull, and they are practically screaming for just one more electron to perfectly fill their outer shell.
Section 5. Ionic and molecular compounds. Rules of attraction.
Which brings us right to the climax of our zoom-out journey. How do these individual atoms actually interact to build the world around us? Well, based on those trends we just covered, we get two main types of relationships. First, ionic compounds. This is usually a metal from the left side of the table, which is large and easily loses electrons, meaning a nonmetal from the right side, which desperately wants electrons. The metal completely transfers its electron to the nonmetal. This creates charged ions that stick tightly together to form solid crystals, like your everyday table salt. Then we have molecular or covalent compounds. This happens when two nonmetals get together. They both want electrons pretty tightly, so neither is willing to let go. Instead, they compromise and share their valence electrons. These tend to be gases, liquids, or soft solids like water or carbon dioxide.
Okay, let's do a quick knowledge check to see if we can apply our new cheat codes. Imagine magnesium, which is a metal sitting over in group 2, reacts with nitrogen, a nonmetal over in group 15. What kind of compound are they going to form, and what exactly will happen to our magnesium atom? Take just a second and think about where they live on the map.
All right, here's the breakdown. Because we have a metal and a nonmetal, they're going to form an ionic compound. Magnesium, sitting in group 2, wants to lose its two outermost valence electrons, so its electron configuration can drop down a level and perfectly mimic the incredibly stable noble gas neon. By losing two negative electrons, magnesium becomes a cation with a 2+ charge. And the nitrogen? It'll gladly snatch those electrons right up. It just perfectly demonstrates the predictive power of the periodic table.
We've covered a ton of ground today, but I really want you to remember this quote from our source material. The specific arrangement of electrons in orbitals of an atom determines many of the chemical properties of that atom. It really all comes back to this. The specific arrangement of almost weightless particles in completely invisible orbitals entirely dictates whether an element is going to be a reactive metal, a toxic gas, or the fundamental building block of life. The microscopic rules literally create our macroscopic reality.
I want to leave you with this final thought to ponder. If shifting just a single, nearly weightless electron can change an atom's entire chemical identity, literally turning a highly explosive metal like sodium into a completely stable ion in the salt you put on your French fries, what other delicate, unseen balances and forces are out there governing the complex macroscopic world you interact with every single day? It really makes you look at everything around you just a little bit differently, doesn't it? Thank you so much for joining me on this explainer. Keep asking those big questions, and I will see you next time.